All right, welcome back. Dr. Pitcher here again, and we should be wrapping up Chapter 7 with this video. And in this lecture video, I want to talk about carbocation rearrangements. Actually, a subtitle for this could be, how do we know what the mechanism of electrophilic addition of alkenes is. Like I said before, we can disprove a mechanism, but we can't conclusively prove. I mean, we can have a lot of evidence supporting a mechanism and, effectively proving the mechanism, but since we usually can't directly observe some of these species, we have to propose mechanisms that are consistent with experimental data. So one interesting bit of experimental data is the follows. So we can do the following reaction. So let's look at here's 3-methyl 1-butene, and we'll go ahead and actually I'm missing a hydrogen here. Actually, I'm not going to show. I'm going to draw it this way. I'll draw it that way. And we'll add HCl. And now Markovnikov's rule tells us that the hydrogen's going to go here and the chlorine should go there. So our product will be However, something interesting happens. We actually get a combination of products here. We get a mixture of products, and it's about 50-50. So we get 2-chloro-3-methyl-butane, and we get 2-chloro-2-methyl-butane, and we get about a 50-50 mixture. Now, how can that happen? So whatever mechanism we come up with has to account for the formation of all the products. So a simple one-step mechanism would not account for this. So like if we just said, oh, these electrons pull off the hydrogen, and then a lone pair from the chlorine goes right there, and we just add HCl all at once across the double bond, we won't get this product. So let's take a look at what might be going on and how it can account for what we see. So let's go ahead here and I'll redraw this just a little differently. So CH3, CH3, C, double bond C, H. Now I'm going to put this guy here in blue, and then I'll put my HCl in red. And I'll go ahead and I'll have my double bond, pluck the hydrogen off the HCl, and then those electrons from the HCl bond end up on the chlorine. And so now I will have CH3, CH3, CH, positive charge there, and there's my hydrogen. Okay, and you know what? I just realized I should have added in my hydrogen. It should be in red there. I apologize. That's in red. And now I've got my Cl minus. And that can come along and then add, and I will get H3C, C, CH3, C, H, C, H, H, H there, and Cl there. I'm not going to show the lone pairs there. Okay, so this accounts for the formation of this guy right here. Now, what if this hydrogen and its electrons jumped over? So we're going to call that a hydride shift. Okay, hydride is a hydrogen with 2 electrons. Okay, so proton is just hydrogen, no electrons. Hydrogen is hydrogen with 1 electron, and hydride is negative hydrogen, so hydrogen with 2 electrons. So if the hydrogen and both its electrons hop on over, then we could get the following. And now our chloride could go ahead and add in there, and we'll get our final product. And I realize I probably should have drawn that in blue. Sorry about that. Trying to color code things so you can keep track of which atoms are going where. But it works better if I remember to use the right colors. I'm deliberately using a black for that line, for that bond going to that hydrogen, because it was those electrons from the CC double bond that pulled off that hydrogen. Whereas this, I've got the blue line because it was the hydrogen and its electrons that hopped over. All right. So this rearrangement, this hydride shift, can account for the 2 products we see. Now there might be other crazier mechanisms that possibly account for it, but this one makes sense. And so the fact that these carbocation rearrangements are observed means that the proposed mechanism is likely to be the correct one. Now notice a couple of things here. Notice that here we have a secondary carbocation, carbon attached to 2 other carbons, and then a hydrogen. And here we have a tertiary carbocation, carbon attached to 3 other carbons. So this would be the more stable intermediate, but the secondary is still stable enough that we actually see it, and it will take some time for this hydride shift to occur. Now we can also see some different types of shifts, different types of rearrangements. So So this one is the hydride shift. Let me just circle that here, hydride shift. We can also get a methyl shift. And that would be something like the following. CH3, CH3, C double bond C, H, H, H. I'll go ahead and have my proton get plucked off. Now I'll have H3C, C, CH3, C, H, C, H, H. I have a positive charge there. There's that hydrogen. And there's my CH3. So I could now have this whole methyl group shift over. And that's going to give me the following. Sorry, my paper's getting a little away from me here. And actually, I should be drawing this guy in blue here. And then that guy is red there. I've got my Cl minus, Cl minus. Forgot the positive charge there for the carbocation. And now I can get my chlorine adding in there. And I'll get my, and then I'll go on and get my final products. Let's see what those would be. H3C, C, CH3, C, H, C, H, H, CH3, ClH, and over here I've got H3C, C, CH3, C, H, C, H, H. Oops, sorry, that's an H, not a Cl. It's getting late. What can I say? That's a Cl. And then CH3. Phew. All right. Sorry if I went through that a little quickly. But we get the methyl shift. So again, we're going from a secondary carbocation here. So carbon attached to two other carbons. Secondary carbocation, methyl group hops over, methyl shift, and now we've got a tertiary carbocation. And there are actually other types of alkyl shifts. And so an example of that could be something like, oh, let me think here for just a minute. You know, I don't think we're going to see the alkyl shifts until we start looking at substitution and elimination reactions. So we're not going to run into them for addition reactions at this point. But they are a type of shift. So instead of just a methyl group, a whole alkyl group could shift over. And we may later on, not for the electrophilic addition mechanisms, but later on with substitution or elimination, we could get primary carbocations, which normally wouldn't form, but we get an immediate rearrangement to something more stable. So the fact that these other products are observed means that we have to go through this carbocation intermediate, because otherwise the molecule wouldn't be able to rearrange. Okay, so this is an example of one of those reactions, rearrangement, appearing as not an entire reaction, but just part of what's going on. All right, so I've talked about, I mentioned alkyl shifts, talked about the methyl shift and the hydride shift. So I guess my take-home message for this lecture is to remember that shift happens. And on that note, stay safe, and I will see you later. Bye now.